Hey everyone, welcome to Advanced Exercise Physiology. Today we'll be covering Chapter 1, the measurement of work, power, and energy expenditure. The objectives of this chapter will be to define the terms work, power, energy, and net efficiency. We will give a brief explanation of the procedure used to calculate the work performed during a cycle ergometer exercise and a treadmill exercise. In addition, we'll describe the concept behind the measurement of energy expenditure using direct calorimetry and indirect calorimetry. Also, we will discuss the procedure used to estimate energy expenditure during horizontal treadmill walking and running. We will define the following terms: kilogram meter, relative VO2, MET, and open circuit spirometry. In addition, we'll describe the procedure used to calculate net efficiency during steady state exercise. For those of you who are taking notes, here is a brief outline that you will be able to follow. Alright, the first thing we want to discuss are units of measure. Now, although this might seem basic, it's very important that we are all communicating and using the same terminology, and even more important than that, understanding what that terminology means. So the first thing we'll address is the metric system. The metric system is the standard system of measurements for scientists. We use this to express mass, length, and volume. Now, although it's what scientists use internationally, in the United States we don't always use the metric system, so it's important for us to familiarize ourselves with the metric system and all the units that it includes. Within that, we use a system of international units. These are the standardizing units of measurements, which we will discuss in just one second. Now, addressing the common metric system prefixes, we'll go down this list real quick and just make sure we're all familiar with them. Mega would refer to 1 million, and kilo would refer to 1,000. All of these would be greater or more than 1. Now, when we have a smaller measurement, we will use centi for 1/100th, milli for 1/1000th, micro for 1/1,000,000th, nano for 1/1,000,000,000th, and pico for 1/1,000,000,000,000th. Please note the numbers and the decimal points associated with each of those prefixes. Now, looking at the SI units within this, we're going to look at mass, distance, time, force, work, energy, power, velocity, and torque. It's going to be really important that we become familiar with these and understanding how each of the units associate with each of the quantifying things that we're going to look at in human exercise. Please take 1 minute just to familiarize yourself with this table and the important SI units. Now, just to recap, the metric system is a system of measurements used by scientists to express mass, length, and volume. In an effort to standardize terms for the measurement of energy, force, work, and power, scientists have developed this common system of terminology called the System of International Units. Again, this might seem very basic, but it's important that we're communicating and understanding the terms that we're using, especially when in the United States we don't always use the metric system for our measurements. So please, again, don't overlook this and make sure you become very familiar with the metric system and the SI units. I'm familiar with the metric system and the SI units. We want to start to define some of the SI units and also understand how to use them in different measurements. The first unit we will address is work. Work is defined or equal to force times distance. If we're looking at the SI units, we have work in joules is equal to force in newtons times distance in meters. Now, how we would apply this measurement is looking at an example where we were lifting a 10 kilogram weight up a distance of 2 meters. Now, we will know from the conversion chart, which will be on the next slide, that 1 kilogram is equal to 9.81 newtons, so 10 kilograms is actually equal to 98.1 newtons. So what we have is 1 newton meter is equal to 1 joule, so 196.2 newton meters is actually equal to 196.2 joules. So when you look at the problem, or the measurement, you have 98.1 newtons times 2 meters is actually equal to 196.2 newton meters. So the answer to our problem is the work in that measurement is 196.2 joules. So in the table below, you're going to be able to look at the common units used to express work and energy. Like I mentioned before, if you have 1 kilogram meter, it's going to be equal to 9.81 joules. There are other examples that are going to make it easy for you to solve problems that pertain to measurements that we look at in the future. So please take your time and familiarize yourself with these common units. Next we will look at power, and power is going to be equal to work divided by time. So in our SI units we have power, which is in watts, is equal to our work, like we just defined, in joules, divided by time in seconds. So when looking at a measurement, we could look at performing 20,000 joules of work in 60 seconds. And we're going to want to define our power at that point. Now, when we're performing 20,000 joules of work in 60 seconds, we simply apply it to the equation that defines power above. So we have 20,000 joules divided by 60 seconds. That's going to be equal to 333.33 joules per second, which is equal to actually 333.3 watts, which would be the actual power. Now, similar to the table that we looked at for energy and work, we're going to look at the table below in a way to express power. So when we were talking about watts, we determined that those were equal to 1 joule per second. So again, please take the time to look at the chart and listing of watts and horsepower, etc., and as well as the conversion table so that you can go back and forth between units when you're calculating measurements on future examples. Work and power, we actually want to talk about how to measure them directly. Ergometry is the actual measurement of work output. An ergometer is the device used to measure work. We can do this in several ways. There's a bench step ergometer, a cycle, an arm, and a treadmill ergometer. The ergometers are used in the measurement of human work output and power. Below you'll see examples of each of these as we've been discussing. The first measurement of work and power will be using the bench step. Subjects are to step up and down at a specific rate. For example, we would have a 70 kilogram subject on a 0.3 meter step, taking 30 steps per minute for 10 minutes. The total work is going to be equal to the force times the distance. So in this particular example, the force is equal to 70 kilograms times 9.81 newtons per kilogram, which is going to be equal to 686.7 newtons. When we look at this problem, we're going to have the distance of the step, which is 0.3 meters per step, times 30 steps per minute times 10 minutes. So the subject will travel a total of 90 meters. By combining the two, we have 686.7 newtons times 90 meters is going to be equal to 61,803 joules. Conversion again, we can convert the 61,803 joules to 61.8 kilojoules. But when we look back at the power equation and simply input the numbers that we now have 61,803 joules, which is our work, divided by 600 seconds, which refers to our 10 minutes at 60 seconds per minute, equaling 103 watts. So for this particular measurement, our power is 103 watts. Now looking at a cycle ergometer, it's exactly the same process. The only difference is instead of being on a step, we're on a bicycle or a cycle. The stationary cycle that allows an accurate measurement of work performed. Now instead of using steps, in this particular case we're going to use revolutions, and we're going to use those revolutions per minute. But the same equation is going to be the same, where we're looking to determine the power in watts. Again, you're going to want to familiarize yourself with the units that are involved in determining the amount of power during these type of measurements. Now in this particular measurement, you can see on the third line of calculations that 52,290 joules, again divided by 600 seconds, is going to give us our answer of 88.2 watts. Again, I want to encourage you to look at the conversion tables and familiarize yourself with the different units that you're going to need to be able to solve these particular problems, as we will again look at two more examples, but then you'll also have different study problems at the end of this chapter. The treadmill is going to be another ergometer that we use to calculate the amount of work done. Now, calculation of work performed while a subject runs or walks on a treadmill is not generally possible when the treadmill is horizontal, even though running horizontal on a treadmill requires energy. Quantifiable work is performed when walking or running up a slope. So for the incline of the treadmill, it is expressed in percent grade, the amount of vertical rise per 100 units of belt travel. So in this case, 10% grade means 10 meters of vertical rise for 100 meters of belt travel. So determining the percent of a grade on a treadmill, what you would do is you would look at the vertical rise, measuring the distance from the ground to the lifted axle, and you would divide that by the hypotenuse, the distance from axle to axle, and that would give you your grade. So looking at an example of the amount of work done on a treadmill, we have a 60 kilogram person at a speed of 200 meters per minute at a 7.5 grade for 10 minutes. Now the vertical displacement is equal to the percent grade times the distance. So in this example, the subject will have traveled a total of 150 meters. Now in order to determine the amount of work that was done, we look at the body weight times the total vertical distance. Now we would want to convert the body weight into newtons, which would actually be, for a 60 kilogram subject, 588.6 newtons. Please see the conversion table to understand how that was done. And we're going to multiply that by 150 meters, which would give us an answer of 88,290 joules, or 88.3 kilojoules would be the total amount of work done. Now depending on the type of measurement or the example being used, we could also report the answer in kilogram meters. Again, if you referenced the conversion chart before, 1 kilogram meter is equal to 9.81 joules. So please again remember to familiarize yourself with the units and how to convert between kilogram meters and joules. Again, to summarize, we're looking for an understanding of the terms work and power, and they are necessary to compute human work output and the associated exercise efficiencies. As a reminder, work is defined as the product of the force times the distance, meaning work is equal to force times distance, and power is defined as work divided by the time. The next thing we want to look at is the measurement of energy expenditure. Energy expenditure is going to be measured by two ways, either direct calorimetry or indirect calorimetry. First, we'll look at direct calorimetry. It is the measurement of heat production as an indication of a metabolic rate. Commonly, we measure it in calories. Now we have 1 kilocalorie that is equal to 1,000 calories, and again, looking at our unit conversion, 1 kilocalorie is also equal to 4,186 joules, or 4.186 kilojoules. Looking at a diagram of a simple calorimeter, we have a temperature measurement where we have airflow into a chamber, a circulating jacket of water, and airflow out of the chamber, the measurement of evaporated heat loss. For indirect calorimetry, we have a measurement of oxygen consumption as an estimate of metabolic rate, where we have foodstuffs plus oxygen is equal to the heat plus carbon dioxide plus H2O water. So for a VO2 of 2.0 liters per minute, it's equal to approximately 10 kilocalories or 42 kilojoules per minute. Now this is going to depend on the type of nutrient, carbohydrates, or fats that are metabolized. For open circuit spirometry, we're going to determine the VO2 by measuring the amount of O2 consumed. So VO2 is equal to the volume of O2 inspired minus the volume of O2 expired. This is just a simple diagram of an open circuit spirometer. So in summary, the measurement of energy expenditure at rest or during exercise is possible using either direct or indirect calorimetry. Direct calorimetry uses the measurement of heat production as an indication of the metabolic rate, where indirect calorimetry estimates the metabolic rate via the measurement of oxygen consumption. Now looking at these terms and the expression of energy expenditure, we have VO2, which we mentioned, which is equal to liters per minute. An example would be a 60 kilogram subject. They have a ventilation of 60 liters per minute, where inspired O2 is equal to 20.93%, where expired O2 is equal to 16.93%. So again, we have a 60 liter per minute times 20.93% minus 16.93% is ultimately going to equal 2.4 liters per minute for our VO2. Now calculating kilocalories per minute, where we have an example of, again, our VO2 of 2.4 liters per minute, where 1 liter of O2 is equal to 5 kilocalories per liter. Now this ranges from 4.7 kilocalories per liter for fats to 5.05 kilocalories per liter for carbohydrates. So if we have 2.4 liters per minute times 5 kilocalories per liter of O2, we end up with a total of 12 kilocalories per minute. Now, over a course of 30 minutes, we have 12 kilocalories per minute times 30 minutes equaling 36 kilocalories. Combining it, if we look at our VO2, which can now equal milliliters per kilogram minute, you have an example again of your VO2 equaling 2.4 liters per minute. Again, our body weight was 60 kilograms. So with our 2.4 liters per minute times 1,000 milliliters per liter divided by 60 kilograms, our total VO2 equals 40, or milliliters per kilogram minute. Now as we move on to METs, the MET is equal to the resting metabolic rate, which is typically 3.5 milliliters per kilogram minute. So in our previous example, we had a VO2, which is equal to 40 milliliters per kilogram minute. So if we have 40 milliliters per kilogram minute divided by 3.5 milliliters per kilogram minute, we end up with a total of 11.4 METs for our example. Now combining that with kilocalories per kilogram hour, and again using our example, we have a VO2 of 40 milliliters per kilogram minute. We have 1 liter of oxygen at 4.85 kilocalories per liter of O2. This is a mixture of carbohydrates and fats, if you remember our breakdown from before. So at 40 milliliters per kilogram minute times 60 minutes per hour, we end up with a total of 2,400 milliliters per kilogram hour, which is also equal to 2.4 liters per kilogram hour. Now combining the calculations, we have 2.4 liters per kilogram hour times 4.85 kilocalories per liter of O2, which is equal to 11.6 kilocalories per kilogram hour. Now again, in summary, energy expenditure can be expressed in liters per minute, kilocalories per minute, milliliters per kilograms per minute, METs, and kilocalories per kilogram hour. Please don't get confused by all of the different expressions of units that might be necessary. Now, with all that put together, what I was trying to get across is that energy expenditure can be measured in a number of different ways, and we can express it as either liters per minute, kilocalories per minute, milliliters per kilogram per minute, METs, or kilocalories per kilogram hour. All of them are looking at the exact same thing with its energy expenditure. This again points back to the fact that we're going to need to maintain our familiarity with the different units and things that are being expressed, and to not get confused, but to just pay attention to the measurements for our calorimetry so that we can accurately express energy expenditure in any type of unit. Now to convert liters per minute to kilocalories per minute, we simply are going to multiply it by 5 kilocalories per liter. Now to convert liters per minute to milligrams per kilogram minute, simply multiply it by 1,000 and then divide by the body weight in kilograms. And finally, to convert milliliters per kilogram minute to METs or kilocalories per kilogram hour, just divide by 3.5 milliliters per kilogram minute. If you simply follow those simple rules, again like with the other units, you'll easily be able to go back and forth and express energy expenditure. Next, we want to take a look at the estimation of energy expenditure. If we look at the energy cost of a horizontal treadmill walking or running, the O2 requirement increases as a linear function of speed, which is meters per minute. The estimation of walking is going to be VO2 milliliters per kilogram minute equal to 0.1 times meters per minute plus 3.5, while running is going to be VO2 milliliters per kilogram minute equal to 0.2 times meters per minute plus 3.5. Please take a moment to look at the relationship between walking or running speed and VO2 in the graph below. Again, you will note that both of these are a linear function. So in summary, the energy cost of a horizontal treadmill walking or running, or cycling for that matter, can be estimated with reasonable accuracy because of the O2 requirements increasing again in a linear function of speed and power respectively. Now if we take a closer look at the estimation of the O2 requirement of treadmill walking, we'll see that we have a horizontal component and a vertical component. So for the horizontal VO2, again we have 0.1 milliliters per kilogram minute divided by meters per minute times the speed, which again is meters per minute, plus 3.5 milliliters per kilogram minute. But we also have a vertical VO2 component, which is 1.8 milliliters per kilogram minute times the speed times the percentage grade. Now note, if we don't have any grade and we're simply running or walking horizontally, walking in this case, the grade would be 0 and there would be no vertical component. But for the example that we're going to look at, we're going to be walking at 80 meters per minute at a 5% grade. So the horizontal VO2 component would be 0.1 milliliters per kilogram minute times 80 meters per minute plus 3.5 milliliter per kilogram minute equaling 11.5 milliliter per kilogram minute. The vertical component would be 1.8 milliliter per kilogram minute times 80 meters per minute times 0.05 for the percentage grade equaling 7.2 milliliters per kilogram minute. So the total VO2 would be 11.5 milliliters per kilogram minute plus 7.2 milliliters per kilogram minute equaling a total VO2 of 18.7 milliliters per kilogram minute. Now if we look at an estimation of the O2 requirement of treadmill running, let's do an example where we only calculate the horizontal VO2 and eliminate the vertical VO2 component that we looked at in the walking estimation. So for horizontal VO2, again that unit is milliliters per kilogram minute. So the equation for the running would be 0.2 milliliters per kilogram minute divided by meters per minute times the speed, which is again meters per minute, plus 3.5 milliliters per kilogram minute. So in this example, we're running at a speed of 161 meters per minute, which is approximately 6 miles per hour. Now again, we don't have to include the vertical component because we're not running at any percentage of grade. So to calculate or estimate VO2, it's 0.2 milliliters per kilogram minute times 161 meters per minute plus 3.5 milliliters per kilogram minute, which is equal to 35.7 milliliters per kilogram minute. Now if we transition to the estimation of the O2 requirement of cycling, that's going to be comprised of 3 different components. The first is the resting VO2, which is 3.5 milliliters per kilogram minute. The second is the VO2 for unloaded cycling, which is again 3.5 milliliters per kilogram minute, and the VO2 of cycling against an external load, which is 1.8 milliliters per kilogram meter times the work rate divided by the body mass. Now continuing with our estimation of the O2 requirement of cycling, in the equation we're going to have a work rate in kilogram meter per minute, a mass in kilograms, and 7 will be equal to the sum of the resting VO2 and the VO2 of unloaded cycling. So for our example, we're going to have a 70 kilogram man at a work rate of 600 kilogram meter per minute. So our VO2 is going to be equal to 1.8 times 600 kilogram meter per minute divided by 70 kilograms plus 7, which is going to equal a total of 22.4 milliliter per kilogram minute. Now if we look at the relationship between the work rate and the VO2 for cycling, again you'll see a linear relationship. Please review the table to look at this relationship. As we move forward, we're going to look at the calculation of exercise efficiency. The net efficiency is going to be the ratio of work output divided by the energy expended above rest. The net efficiency of cycle ergometry is about 15 to 27%. Efficiency decreases with increasing work weight. So what that means is we're going to have a curvilinear relationship between the work rate and the energy expenditure. Factors that influence this exercise efficiency are going to be exercise work rate. Again, efficiency decreases as the work rate increases. We can also look at the speed of movement. There is an optimum speed of movement, and any deviation from that reduces the efficiency. Also, muscle fiber type affects exercise efficiency. Higher efficiency is seen in muscles with a greater percentage of slow twitch muscle fibers. Now looking at this chart, the net efficiency during arm crank ergometry again shows that with an increased work rate, we have a decrease in exercise efficiency. If we look at the relationship between energy expenditure and work rate, again we have a curvilinear relationship between the two variables. Now if we look at the effects of speed of movement of net efficiency, again we have a curvilinear relationship where there's an optimum speed for exercise efficiency. So moving too slow or too fast is going to affect the overall efficiency of the exercise. In summary, the net efficiency is defined as the mathematical ratio of work performed divided by the energy expenditure above rest, and this is ultimately expressed as a percentage. The efficiency of the exercise decreases as the exercise work rate increases. This occurs because the relationship between the work rate and the energy expenditure is curvilinear. In order to achieve maximal efficiency at any work rate, there is an optimum speed of movement. Again, we've seen all of these relationships in the charts before. Ultimately, exercise efficiency is greater in subjects who possess a higher percentage of slow twitch muscle fibers compared to subjects with a higher percentage of fast twitch muscle fibers. This occurs because slow twitch muscle fibers are far more efficient than the fast twitch muscle fibers. Now, if we move on and we look at running economy, it's not possible to calculate the net efficiency of horizontal running. Running economy is looked at as the oxygen cost of running at a given speed. Lower VO2, which is again milliliters per kilogram minute, at the same speed indicates better running economy. There is a gender difference, but not at lower speeds. At race-paced speeds, males may be more economical than females. The chart below is a comparison of running economy between males and females. Again, you can see as the rate increases, or the running speed for that matter, males may show a slight bit more economy than females. So in summary, although it is not easy to compute efficiency during horizontal running, the measurement of the O2 cost of running at any given speed offers a measurement of running economy. Running economy does not differ again between highly trained men and women distant runners at slow running speeds. However, at a faster pace or race pace speed, male runners may be more economical than female runners. The reasons for these differences at this point are unclear. Now with all of that, I want to review some study questions with you. Again, we've gone over several different calculations, units, and different definitions of terms, and we want to make sure that everybody's clear on exactly how to use these and apply them. So again, please review and define the following terms: work, power, metric system, percent grade, SI units, and relative VO2. Now following the definitions, I know that there was some confusion potentially as we went through different calculations or measurements during this lecture. So the best way to clear up any confusion is actually going to be to practice these calculations and measurements. So please do the following measurements or calculations as practice or study questions. Number 2 would be to calculate the total amount of work performed in 5 minutes of exercise on a cycle ergometer given the following: resistance of the flywheel at 25 newtons, cranking speed 60 revolutions per minute, distance traveled per revolution 6 meters. Question 3. Compute the total work and power output per minute for 10 minutes of treadmill exercise given the following: treadmill gait of 15%, horizontal speed of 90 meters per minute, subject's weight of 70 kilograms. Please briefly describe the procedure used to estimate energy expenditure using A. direct calorimetry and B. indirect calorimetry. Next, compute the estimated energy expenditure in milliliters per kilogram minute during horizontal treadmill walking for the following examples. Treadmill speed equal to 50 meters per minute, subject's weight 62 kilograms. Treadmill speed 100 meters per minute, subject's weight 75 kilograms. And finally, treadmill speed 80 meters per minute, subject's weight 60 kilograms. Next, please calculate the estimated O2 cost of horizontal treadmill running in milliliters per kilogram minute for a 70 kilogram subject at 150, 200, and 235 meters per minute. Next, calculate the power output during 1 minute of cycle ergometer exercise given the following. Resistance on the flywheel equal to 3.0 kilograms. Crank speed 50 revolutions per minute. And distance traveled per revolution equal to 6 meters. Next, calculate net efficiency given the following. Resting VO2 equal to 0.3 liters per minute. Exercise VO2 equal to 2.1 liters per minute, and work rate equal to 150 watts. Finally, compute the oxygen cost of cycling at work rates of 50, 75, 100, and 125 watts for a 60 kilogram person. Again, practice makes perfect on these calculations, so please just be careful to keep track of your units and your conversions, and that should help in the process. That concludes Chapter 1, the measurement of work, power, and energy expenditure. Please again refer to the lesson and/or the textbook if you have any questions, and also feel free to email me at any time.